Hello, everyone, and welcome to the Environmental Finance Center's Wastewater Treatment Works educational video series. My name is AJ, and I'm a research engineer with the Southwest Environmental Finance Center. In today's educational video, we will be learning about advanced wastewater math concepts that are used to evaluate activated sludge processes. Specifically, we are going to learn about mean cell residence time, some supporting concepts, and practice calculating the mean cell residence time of an activated sludge treatment system. Mean cell residence time is usually abbreviated as MCRT and is a parameter of wastewater treatment that is used to describe the amount of time that microorganisms spend in the wastewater treatment system. MCRT is an important activated sludge parameter that helps operators understand how long microorganisms remain active in the treatment process, influencing the efficiency of biological treatment. It is then used to determine the rate of wasting and rate of reuse of solids that is appropriate from secondary clarifiers. It is important to make adjustments to the MCRT to maintain a balanced sludge age and ensure the microbial community is not too old or too young. When sludge is allowed to reside in the activated sludge process for too long, it can lead to less efficient treatment and settling issues due to sludge bulking or because old sludge tends to settle too quickly. When the sludge's MCRT is too short and the sludge is considered too young, wastewater treatment will be incomplete, which correlates to the activated sludge having a lower than desired biomass. Another parameter that can be used to determine wasting and reuse rates is solids retention time, or SRT, which describes the amount of time solids spend in the activated sludge treatment process. SRT was previously more widely used than MCRT, but from what I have seen, state operator certifications typically utilize MCRT more frequently. There are many instances when the equations are used interchangeably in reference material as well, and it is important for anyone using this video as a study guide to make sure they compare the equations we use and the equations they need to be using and make adjustments as needed. Now that we know a little bit about MCRT, here are the terms and some of their typical units typically used to calculate the MCRT. It should be noted that different units of concentration, mass, or volume can be used, and we will explore this more later in the video. The first term we should know is MLSS, which stands for mixed liquor suspended solids. This is the suspended solids portion found in the mixture of activated sludge, raw wastewater, and returned sludge found in an aeration tank known as mixed liquor. This is typically measured using a probe in the aeration tank or through lab analysis. Then there's waste activated sludge, which is represented by the acronym WAS and represents the amount of excess microorganisms and solids removed as sludge from secondary clarifiers to maintain balance for the biological system in the activated sludge process. I would like to note that the acronym for waste activated sludge can be pronounced as either WAS or WAS. And when I was trained as an operator, I learned it as WAS. So if you're used to hearing WAS, just remember I am talking about the same thing. Next, there's the volume of the aerator and secondary clarifier, which is provided in design documents for wastewater treatment systems, or in the case for wastewater operator certifications, may be something that needs to be calculated. Then there's the flow of the effluent from the plant and the WAS being wasted from the system. These are measured in millions gallons per day or gallons per day typically. Finally, there's the total suspended solids, which represents the solids concentrations found in the effluent and WAS flows. Total suspended solids is abbreviated as TSS and has the same units and is typically measured in the same way as MLSS. Now that we understand the terms and their abbreviations that we will be using to calculate MCRT, here's the equation that we will use. It's important to remember that we solve the operations in parentheses first, followed by the separate terms in the numerator and denominator, and finally divide the total of the numerator by the total of the denominator to calculate our MCRT for the whole equation. So based on that, we multiply the MLSS concentration by the sum of the volume of the aerator and the volume of the secondary clarifier. We then add the product of the TSS concentration multiplied by the wasting rate with the product of the TSS concentration of the final effluent multiplied by the flow of the plant effluent. We then take the calculated value found from our terms on the top of the equation and divide that by the value calculated from the terms on the bottom of the equation. And this will result in our MCRT value, which is reported in days. Some typical MCRT values for conventional activated sludge processes are 3 to 15 days. And for extended aeration activated sludge processes, it's 20 to 40 days. Now, I've also included the typical SRT equation, which if you compare to the MCRT equation, you can see it does not account for the volume of activated sludge present in the secondary clarifier. Some of you may still find this equation useful, but like I mentioned earlier, I would also suggest that if you are asked to calculate SRT, you should verify what equation you're being asked to use on your reference sheet or on your certification test. Because like I mentioned earlier, some resources use the two interchangeably, or they also will mix them around. Now that we've gone over the equation and know our terms that we're going to be using, let's go over the sample problem and identify the parameters we're going to be using to calculate MCRT. So sample problem 1 reads, you have been asked to calculate the MCRT of a small wastewater treatment plant with an average daily flow of 1 million gallons per day. You are given design specifications for the plant, which indicates that the volume of the aeration tank is 380,000 gallons, and the volume of the secondary clarifier is 95,000 gallons. You run some analysis to find the remaining values needed to calculate the MCRT for the plant. Using the treatment parameters provided below, calculate the MCRT for the plant and identify if this is in the desired range for a conventional activated sludge treatment plant. And then we are provided the following values: an MLSS of 3,505 milligrams per liter, a WAS flow rate of 55,000 gallons per day, a final effluent TSS of 7 milligrams per liter, and a WAS TSS of 5,563 milligrams per liter. And I've also included the equation for our MCRT so we can use the values in the sample problem to make sure that we have everything we need in our equation to calculate the MCRT. So the first thing I see is the average daily flow of 1 million gallons per day, which is going to equate to our effluent flow because the effluent flow is not explicitly stated. So we will assume whatever's going in is what's coming out. Next, we have the volume of the aeration tank at 380,000 gallons, which correlates right here in the equation for volume of the aerator. Next, there's the volume of the secondary clarifier of 95,000 gallons, which correlates to this term, volume secondary clarifier, on the equation. Then there is the MLSS, which is given in the parameters that we calculated, correlates to right here in the equation. The WAS flow, which would probably get from a meter, which is right here in the equation. Next, we have the final effluent TSS, which is going to be right here. And this correlates right here in the denominator. And then finally, there's the WAS TSS, which is going to go right here. With that, we have identified all the terms that we're going to need in our equation, and we can move on to solving the problem. So I went ahead and brought all the values over that we identified in the problem, so we can go ahead and start plugging those into the equation to solve for MCRT. This will be multiplied by the sum of the aerator volume of 380,000 gallons, or 0.38 million gallons, added to the secondary clarifier volume of 95,000 gallons, or 0.095 million gallons. And I converted this to millions of gallons to get rid of some of our extra digits. And this is simply done by dividing 380,000 gallons or 95,000 gallons by 1 million. Next, we're going to plug in our terms in the denominator. And the first one in parentheses is our WAS TSS, which is 5,564 milligrams per liter, which is multiplied by the WAS flow of 44,000 gallons per day or 0.044 mgd. And this is added to, in parentheses, the final effluent TSS of 7 milligrams per liter multiplied by the plant effluent flow of 1 million gallons per day or 1 mgd. Now, the next step, we can go ahead and start simplifying the problem. So we're going to first have 3,505 milligrams per liter. And we're going to go ahead and solve for what was in the parentheses in the numerator, which we get 0.475 mg. In the first term that we solve for, which is the first set of parentheses in the denominator, we get 244.816, and the units are milligrams per liter and millions gallons per day. And this is added to the second term of the denominator that we solve for in parentheses, and that's going to equal 7 milligrams per liter times millions of gallons per day. So we'll go ahead and solve for the top and the bottom. The top is equal to 1,664.875, and the units are milligrams per liter and mg, or millions of gallons. And solving for the bottom is 251.816, and again, the units are milligrams per liter and millions of gallons per day. And then we can start canceling out our units. So the first one that cancels out is the milligrams per liter, and the second is the millions of gallons. And that leaves us with no units on the top, and on the bottom, it's 1 over days. And to show you how to do this, we'll go ahead and set up the problem. So on the top, there's no units, so that's equal to 1. And on the bottom, like we said, is 1 over days. And whenever you are dividing by a fraction, that fraction comes to the top of the term, and the denominator and the numerator switch places. So this becomes 1 day. And if you input the numbers in the equation, 1,664.875 divided by 251.816, it is equal to 6.61 days. So as you can see here, we worked out the solution in advance, and it's the same thing that we got just now, 6.61 days. And this is within the range of 3 to 15 days. So our calculated MCRT is within the desired range. Finally, we have the equation for calculating our waste target, which is just the MCRT equation rearranged. As you can see here, you plug in the desired MCRT with all the values we found before, and this will give you your target wasting rate. And that concludes our basic walkthrough of an MCRT problem, but we are going to provide an additional couple of examples if you would like to continue following along for the rest of the video for more practice. Our next problem will involve calculating the MCRT when the volume of the aeration basins and the clarifier are not explicitly given and instead must be calculated from the dimensions measured. So this problem reads, a small package wastewater treatment plant has a daily average flow of 35,000 GPD. The operators currently waste at a rate of 1,500 GPD. Analysis results show that the average MLSS in the aeration basins and the secondary clarifier is 4,200 milligrams per liter. The effluent TSS is 9 milligrams per liter, and WAS concentration is 6,000 milligrams per liter. The dimensions of the aeration basin and secondary clarifier are not provided with the design documents, so you decide to measure them. The aeration basin has a length of 16 feet, width of 12 feet, and a depth of 10 feet. And the clarifier was measured to have a diameter of 12 feet and a depth of 10 feet. So what is the MCRT of this wastewater treatment plant? So again, I provided our MCRT equation so we can verify if we have everything we need to calculate the MCRT. So we do have the daily average flow, which again is the effluent flow, the wasting rate of 1,500 gallons per day is the WAS flow, and then we have our MLSS concentration right here, the effluent TSS right here, the WAS concentration right here, and we don't have the volume of our aerator or the volume of our secondary clarifier, but we can use the dimensions to calculate it on our next couple slides. So to calculate the volume, we need to know how to calculate the volume of a rectangle, the volume of a cylinder, and then also to do volume conversions. So for the volume of a rectangle, it is the length times the width times the depth. And we had all of those in our equation because we measured them. And then to find the volume of a cylinder, we multiply the height times pi times the whole term of the diameter squared divided by 4. And then another important term that we didn't know is that 1 cubic foot is equal to 7.48 gallons. Now we'll go ahead and calculate the aerator and clarifier volumes using those equations. So first, we have the volume of the aerator, which is equal to length times width times depth, which is 16 feet for the length, 12 feet for the width, and 10 feet for the depth. Now we multiply all those together, and we get 1,920 cubic feet. It's important to remember that when you multiply a foot times a foot times a foot, you get a foot cubed, which is a cubic foot. So now we're going to convert this cubic feet into gallons. And we do this by multiplying our 1,920 cubic feet by our conversion unit, which is 7.48 gallons over a cubic foot. Which if you remember, a cubic foot is equal to 7.48 gallons. So when you put them in a fraction together or a unit conversion, they're basically like multiplying times 1. And we can cancel out the cubic feet on the bottom of that unit conversion with the cubic feet in our term 1,920 cubic feet. So this equals 14,361.6 gallons. Then we're going to go ahead and do the same thing with our secondary clarifier, which if you remember, the volume of a secondary clarifier is equal to a cylinder, which is the height times pi times the term of the diameter squared over 4. And this is equal, if you remember, the height was 10 feet. We're going to use 3.14 for pi, and our diameter is 12 feet. So when we plug that in, we're going to equal 1,130.4 cubic feet. And then we're going to go ahead and use our conversion factor again, and we're going to multiply 1,130.4 cubic feet times 7.48 gallons over cubic feet. And now I'll go ahead and show you where the conversion cancels out units. On the top, the cubic feet will cancel out the cubic feet on the bottom of the conversion unit for the volume of the aerator, and same for the volume of the secondary clarifier, leaving us only with gallons. So now that we've calculated the aerator volume and the secondary clarifier volume, we have everything we need to calculate our MCRT. The first thing we're going to do is plug in our MLSS, just like we did in our previous equation. And this is going to be multiplied by the sum of the aerator volume and the volume of the secondary clarifier. And then in our denominator, we're going to have the WAS TSS multiplied by the WAS flow. And we're going to add this to another term in parentheses, which is the final effluent TSS multiplied by the final effluent flow. We plug this into our calculator, and we get 10.3 days. And again, this is within that 3 to 15 days suggested MCRT for an activated sludge process. And again, we went ahead and worked out the problem in advance. And you can see that we got the exact same answer, 10.3 days. And that wraps up our second problem. And we'll move on to our third now. So here's sample problem 3, where we can practice using units that we haven't used before. So sample problem 3 reads, you are tasked with providing some calculations for a larger wastewater plant that is frequently exceeding their biochemical oxygen demand, or BOD, of their permit limit. But some of their data is presented in a way that is unfamiliar to you. You are told that the wastewater plant has 4 aeration basins and 4 secondary clarifiers that are all currently in operation. You decide to calculate the MCRT to address these BOD issues and are provided the following data. The flow of the plant is 19.4 mgd. The wasting rate for the plant is 15,000 pounds per day. The MLSS is equal to 2,035 milligrams per liter. And this would be for the aeration basins and the secondary clarifiers. And then the effluent TSS loading is 2,200 pounds per day. You're also given the volume for a single aeration basin as 220,000 gallons. And for a single secondary clarifier, the volume is 105,000 gallons. Now, the first thing for this equation I noticed is that they mentioned that there's 4 aeration basins and 4 clarifiers. And we were given the volume for a single unit each. Now, the volume of the aerator, we will go ahead and multiply the 220,000 gallons times 4 to get the total volume of aerator, which is represented by V sub A as 880,000 gallons. And we do the same thing for the clarifier, which is represented as V sub C of 105,000 gallons times 4 for a total of 420,000 gallons. Now, if you'll notice, I can plug these into the equation because I have everything I need now, but the units don't add up. We have milligrams per liter and gallons in our numerator and pounds per day on our denominator. Now, the easiest thing that I think to do is to convert the milligrams per liter and gallons to pounds. But we don't know how many pounds that is, and therefore we don't know how many days the MCRT is. But we'll go ahead and calculate that, and I'll show you how on the next couple slides. Now, in order to convert from milligrams per liter times gallons to pounds, there's a couple terms we need. And the first is 1 gallon is equal to 3.785 liters. And 1 kilogram is equal to 2.205 pounds. Then I want to add the volume of the aerator to the volume of the clarifier to have a total volume. So I only have one term to use when I am converting my units. So we add the total volume of the aerators that we found in the previous problem, 880,000 gallons, to 420,000 gallons of the volume of the total clarifiers. And this is equal to 1,300 gallons. Then I'm going to go ahead and start my unit conversion. So I'm going to plug in my 2,035 milligrams per liter. And the first part of it I'm going to cancel out or convert is my milligrams. So 1 kilogram is equal to 10 to the 6th milligrams. The milligrams on my conversion unit will go on the bottom, so I can cancel it out of my first term. Then I'm going to convert kilograms to pounds, and 1 kilogram is equal to 2.205 pounds. And in this term, kilograms will go on the bottom, or our denominator. Next, because I have pounds in my units, which I'm going for, I need to cancel out the volume. So 3.785 liters is equal to gallons. So the liters on the numerator of this unit conversion will cancel out the liters on my first term. Then I'm going to plug in that volume that we just found. And this will have gallons in my numerator, which will cancel out the gallons on the denominator of my previous unit conversion. So I'm going to go ahead and cancel these out. Milligrams cancels out milligrams. Kilograms cancels out kilograms. We're going to leave pounds alone because that's what we want to end with. Liters cancels out liters. Gallons cancels out gallons. And when we multiply this across, we get 22,079.1 pounds. Now we can start plugging these terms into our solution. So first we have the 22,079.1 pounds that we just calculated from the volume of the aerator and the clarifier multiplied by the MLSS of both. We're going to go ahead and plug in the 15,000 pounds a day that are being wasted, which is added to the 2,200 pounds a day of effluent TSS that is loaded into the receiving waters. And we'll go ahead and keep our 22,079.1 pounds in the numerator, but we'll add our bottom terms in the denominator, which equals 17,200 pounds a day. And then when we cancel these units, pounds goes away, and we know that when we have a unit and the bottom of a fraction in the denominator, that it will then move to the top and be our regular unit. So this 22,079.1 pounds divided by 17,200 pounds per day is going to equal to 1.28 days. And this low MCRT would correlate to less treatment and explain why the plant is having BOD issues. And that is going to wrap up our third problem for our solution. Next, we're going to run over a sample problem, but I'm not going to walk you through it. I'm just going to provide the problem, and then I will provide the solution. Okay, here's sample problem 4. You are asked to assess the MCRT of a 1 MGD wastewater plant. You're provided flow and concentration data, but the dimensions of the activated sludge processes are not provided. You find that there are 3 aeration basins, each with a length of 60 feet, a width of 20 feet, and a depth of 12 feet. You also find that there are 2 secondary clarifiers each with a diameter of 12 feet and a depth of 10 feet. Using these measurements with the following data, please find the MCRT. So the MLSS is provided as 2,621 milligrams per liter. The effluent TSS is 16 milligrams per liter. The WAS flow is 30,000, and the WAS TSS is 7,300 milligrams per liter. So here's the first part of our solution. And I'd like you to notice that I did multiply by 3 different aeration basins as given in the problem. And there are also 2 clarifiers. And what I did is I calculated the cubic feet, I converted it into gallons, and I converted that into millions of gallons for both volumes. And here's the final solution where we plug in all our values and our calculated values. And the MCRT for this specific example would be 4.63 days. And that is the end of our video. We want to thank you for joining us today. Please feel free to comment below if you have any questions. Press the like button if you enjoyed this walkthrough, and subscribe for future videos.